Hi, I'm Yu-chan. Today I'm gonna talk about privilege escalation using DOP in x86 macOS. This presentation is already presented in HITB Amsterdam. Before starting the presentation, let me introduce our team. We are Team GIG and we focus on CTF and bug hunting. Originally, we are a team that only did CTF, but recently we started doing our own research, so we are also doing bug hunting. The team members are all from companies except for me, who is in academia. I think that's enough introduction, so let's move on to the main content. Before introducing DOP technique, we should know how the exploit techniques are developed. In the figure, you can see how exploit technology and mitigations have evolved in application and kernel. Since our topic is kernel exploit, let's take a look at the kernel side. The first one is return to user. Back in the day, the user memory address and the kernel memory address are separated, but the separation was to prevent access to kernel area addresses when the code was executed in the user area. In other words, user area memory was accessible when the code was executed in the kernel area. An attacker could take advantage of this to use user space memory when triggering exploit primitives such as counterflow hijacking. For example, for privilege escalation, the attacker keeps the shellcode in user space and replaces the instruction pointer register with user space, or keeps the RP gadgets in user space and replace the stack pointer register with user space. To prevent return to user, which use a user space memory for privilege escalation, the SMEP and an SMAP are designed. This mitigation prevents to access the user space memory when the kernel code is executed. The return to direct map is a technique that was invented when the user area was unusable. In the kernel, there is a direct map that is the same as user space memory. The attacker used direct map to store shellcode or RP gadgets and exploit by using them. In the past, this direct map had read-write execute permissions. For mitigating, the kernel developers changed the permission only have read and write permissions. After that, the attacker tries to use return-oriented programming. This technique is very popular, so I won't bore you with it. The kernel address space layout randomization is a mitigation that randomizes the kernel memory layout. Since KSLR randomized at boot time, RP which use a specific memory address is mitigated. After the KSLR is widespread, the privilege escalation needs additional steps for bypassing KSLR. It is information leakage exploit. If the attacker leaks one kernel text pointer, the RPOC can be calculated. As RP continues to flourish due to information leakage, counterflow integrity mitigation was developed. This mitigation constrains our counterflow changes at the point where they occur, so they can't jump anywhere. If this mitigation is widespread, the RP technique will fade. The latest exploit technique is data-oriented programming, which is our main subject of this presentation. DOP is popular technique in academia, but it does not get noticed in industry. However, this is not to say that the technique is not used at all. Some vulnerabilities are exploited by using this technique. However, I think they use this technique without the knowledge of this technique, because there is no mention about DOP in their blog post. It's just my opinion. I don't know whether they have knowledge of this technique. DOP is a technique for manipulating data flow to read or write. If the data flow points normal object, DOP manipulates its data flow to point another security critical object. That is, it has advantage when corrupting specific data. Let's talk about the strengths of DOP. DOP is more specialized in kernel exploit than user application exploit. This is because the goal of user application exploit is executing another application. That is, it must involve executing function. On the other hand, the goal of kernel exploit is write 0 to thread structures UID element. Therefore, DOP, which read or write to specific data, is fit into the kernel exploit. The second strength is that DOP is a patch agnostic exploit. As you know, RP exploit is highly affected by the patch. This is because the patch relocates the offset of the RP gadget. On the other hand, DOP is less affected by the patch. DOP gadget is unaffected unless the patch changes the structure of the DOP gadget. This allows DOP to create patch-agnostic, reliable exploit. Privilege escalation exploit using DOP needs 3 exploit primitives. I will explain why each one is necessary. The first is information leakage. In the case of RP, the attacker needs to leak the pointer in the text area to figure out the RP gadget. In the case of DOP, however, the attacker needs to get an arbitrary heap pointer because most DOP gadget objects is placed in the heap area. Therefore, using memory corruption and the kernel user transfer function, the attacker needs to leak a heap pointer. After leaking heap pointer by information leakage exploit, the attacker needs to find the address of CRED object. Please note that the kernel exploit using DOP is writing a 0 to CRED UID element. Therefore, the attacker recursively triggers arbitrary address read primitive to find the address of CRED object. Lastly, the attacker triggers arbitrary address write to write 0 to CRED UID. With these 3 primitives, the attacker can exploit privilege escalation. I think we have enough to talk about DOP. Now, let's move on to the main content. In this presentation, we will introduce one heap buffer overflow bug. Someone think this bug is too old to present in 2023. But as you can see, this bug is unloaded in patch notes in March this year. We first found this bug at 2018 and exploited it in 2020. Why we spent 2 years is we don't have free time because I become a PhD student, so that I spend a lot of time for writing a paper. After exploited, we report to the vendor Apple, but they did not respond about this vulnerability since 2022. In 2022, we can notice this bug are in patch process and give me a CB number. They said it will be uploaded in the patch note, but they does not answer when the patch note is uploaded until 2023. They just told me wait a moment. However, we decided to present this bug rather than wait for it to be uploaded to the patch notes. The attack surface of our bug is related to the Wi-Fi kernel module, that is IO80211 family and Broadcom kernel extension. Family kernel extension communicate with user application and send a request to Broadcom kernel extension. And Broadcom kernel extension communicate with the device. As you see, the kernel extension is different between the architecture of the macOS. They do same operation but slightly different. The fewer functions are available for kernel modules on ARM. This attack surface is not the first time to disclose. It is disclosed in GDI blog post and presented at the Black Hat conference. Regarding GDI blog post, it is a report based on my vulnerability report. That is GDI upload my report. Not that it matters, but I just wanted to say that I was the first to disclose this attack surface. In this attack surface, we found a number of bugs and vulnerabilities. For the vulnerabilities, we reported it and get a bounty, but we did not report bugs. That is, there is a number of bugs left in the wild. I found this attack surface in 2017 and it still has a number of bugs. Therefore, we think it is still a rare attack vector. After finding this module, one question popped in my mind. At first look, they seemed vulnerable, but the premise is that the user should be able to call them. I don't know how other people figure out if the user can call it or not. But in my case, there are two ways to do it. The one is trace back to the root function. If the root function is related to the system call, the user can call the vulnerable function. The second is finding the function regarding user kernel communication. Did you guys know the key function related to the user kernel communication? Here is a good tip for many kernel hackers who are hard to judge what specific functions can be called. It is finding the kernel user data transfer function. This function must include user memory addresses as an argument. It means this function is highly likely triggered by the user. I can't guarantee that this is always the case because some functions only can be triggered by root privilege. But in my case, I was able to invoke it from the user in most cases. However, this method has a problem. Determining this function can be triggered is fine. However, the problem is that it is hard to know which system calls are involved in triggering this function. I've spent a few days with this problem myself. I didn't figure out how to connect to the kernel extension, so I googled the name of the function and I found some example code for connecting and triggering the function in the kernel extension. The example code is simple. It calls socket function and the IO controller function. The vulnerabilities in this presentation are caused by setIE and getIE functions. These two functions can be called by using IO control functions. The setIE function is responsible for storing the information element on the heap, and the getIE function is responsible for fetching the stored information element to the user, and the bug is triggered when executing getIE function. At setIE function, the function stores the information element in vendor IE by using storing function. At this point, the important variable is the length of the information element. That is, the length is also stored in vendor IE element. Please remember this point. The length is stored in vendor IE. Then from getIE function, the kernel allocates the buffer, and the size of the buffer is user controllable. And using allocated buffer, it calls Broadcom NIC's getIE function. The important thing here is the allocated buffer size. Please note that the buffer is allocated with a user controllable size. And let's follow the setIE in Broadcom NIC kernel extension. It gets a buffer from vendor IE, and it executes memory copy function from stored buffer to newly allocated buffer. But the length field of the memory copy function is something strange, as you can see. The length from the stored buffer is used as an argument. The simplified mechanism of this bug is following. Let's suppose the length of the buffer stored by the setIE function is 100. And suppose that the newly allocated buffer size is 80. The memory copy function uses a stored buffer length field as a size, and it will cause a buffer overflow. Because the size of the allocated buffer is 80, but the copy size is 100. Let's summarize the vulnerability. Since the kernel allocates the buffer with user controllable size, the size of the kernel heap buffer is controllable. Further, the length field of the stored buffer is also controlled by user. That is, how many bytes to overflow can be controlled. However, we faced the problem after heap buffer overflow. Since the overflow modified the length element in vendor IE object, the copyout function triggers hardened copy mitigation. The hardened copy mitigation is for preventing overread when executing the copyout function. If the copied size is bigger than the size of the object, it triggers kernel panic. At first glance, we thought this mitigation made it impossible to exploit. This is because the length element must be larger than the size of the object in order to cause an overflow. After thinking about it for a few days, we are able to come up with a little trick. There is two copyout function, and the second copyout function cause a kernel panic. At this point, the important thing is condition. After the first copyout function, if the first copyout function returns fails, the second copyout function is not executed. So we try to find out when the copyout function returns fails. The copyout function returns fails when the copying operation has a problem. The first case is the user space memory address is not assigned. It returns fails. And if the permission of the user space memory is read-only, so that copying is failed, it returns fails. For the first case, we determine it is not applicable to our bugs. This is because getIE function first executes copying function to the same memory space as the argument of the copyout function, so that the memory must be assigned. For the second case, we determine it can be possible applying to our case. Read-only permission returns success to the copying function, but returns fails for the copyout function because writing a value to read-only memory is failed. Let's back to the code. If we assign user space memory with read-only permission, the first copyout function returns fails, and the second copyout, which triggers kernel panic by hardened copy, will not be executed. In other words, we can bypass the hardened copy mitigation by using simple trick. As we bypass the hardened copy, we now can corrupt the target object, which is placed right after the vulnerable object. Now, what do you think is the important part here? The answer is target object. According to which target object is used, the various exploit primitive can be triggered. Therefore, finding suitable target object is very challenging and important. As a side, there is no work that tries to find a specific type of target object. Maybe the famous hackers memorize target object or have a method to find a suitable target object. Back to the point, we discussed earlier that we need 3 primitives to perform a privilege escalation exploit by a DOP. Information leakage, arbitrary address read, and arbitrary address write. At the time, it was my first DOP exploit, so it took me a while to find the target object. Then I came across this post from Google Project Zero. The post introduced one use-after-free vulnerability and the details about exploitation. Coincidentally, this vulnerability was exploited using DOP. Here is the object, which is the vulnerable object for use-after-free bug. By using min MTU, it can leak the kernel pointer, and by using IP6 PO packet info, it can trigger arbitrary address read and write. When I found this object, I was very surprised because one single object has all 3 primitives needed for DOP. But since we only have overflow primitive, we use packet info for 3 primitives: information leakage and arbitrary read and write. Before trying to exploit, the most important issue is which zones the target object is placed. Similar to the Linux kernel, macOS and iOS use zone for performance and security. There is a dedicated zone and a general zone, but in this presentation, we only introduce a general zone. A general zone is used by kalloc function, and according to the size of the object, which zone to be allocated is determined. IP6 packet options is allocated in kalloc 192 zone, and IP6 packet info is allocated in kalloc 32 zone. Since IP6 PO packet info left for the kalloc 32 zone, we spray the mock task self object on kalloc 32 zone. Then overflowing 17 bytes to override the first byte of IP6PO packet info pointer. If the overwritten pointer points mock task self object, we can leak port address. After leaking port address, now we can fully override a pointer for arbitrary address read. However, our target is CRED object, so we have to do recursively arbitrary address read primitive. First is leaking K object in IPC port object. K object points task structure. After leaking task structure, we have to leak BSD info, which is process structure. And lastly, we leak the pointer of uCred structure. It means now we can know the address of CRED objects. As a final, we use arbitrary address write 0 to the CRED UID element. It means the privilege escalation is finished. Here is the proof of concept video. Please note that this is really fast to trigger the privilege escalation. Yeah, it recursively leaks the specific object and write 0 to UID. And this is the end of my presentation. If you have any question, please feel free to email me. And thank you for listening.